Hello and welcome to another data management video. Today we're going to teach you how to create a NetCDF file using Python. If you're not familiar with Python and if you've not done this before, don't worry, we're going to take it step by step. We're going to go really slow. The aim here is to show you that creating a NetCDF file using Python is relatively easy and it's something that you can do too. Because I'm going to be taking it step by step, this video is a bit longer than usual, but hopefully you'll find it useful. And hopefully when you're creating a NetCDF file yourself, you can come back to this video and use it as reference. So hit subscribe and you'll be able to find it again later. Today we're going to be creating a NetCDF file for a depth profile of data, for example from a CTD. Before we get started, we're going to go through some things that you're going to need that are going to help you do this so quickly. They're not anything out of the ordinary, not anything that you shouldn't be doing already if you're making any other data set, but just good housekeeping. So firstly, we have the data themselves. I've created a file here and we have three columns. We have the depth, we have the practical salinity, and we have the temperature. And we can see here I've highlighted in red one cell where we have a missing value, so no temperature was recorded for this depth. In the same Excel file, we have another sheet called global attributes. So global attributes are the metadata that describe the data as a whole. So we have one column here called attributes, and we have another column called value. So the attribute column is the name we're going to assign for each metadata term, and the value is the value that we're going to write for each of those terms. These values are all compliant with the ACDD conventions, so that's the attribute conventions for data discovery. They tell us exactly what terms we should include, what we should be calling each of those terms, so the attribute names, and also some recommendations on how we should be filling in each of those terms. We can also see that this dataset is going to be compliant with the CF conventions. They're the climate and forecast conventions, and I'll come back to those very shortly. But about the global attributes first, we can see that this is a long list of terms. I'm not going to go through each of those individually now, but what I will point out is that there's a few missing terms here. One of them is the date created, and we're going to write that term as we're creating the file in Python. That's because we're going to want the timestamp that we're actually creating the file at. And also the history, which is a log of any updates that we're applying to the file. That should also include the timestamp. It's also useful to have open the different pages for the conventions that we're going to follow. So this is a page with the attribute conventions for data discovery. Briefly, this is where the list of terms can be shown. There's highly recommended terms and also recommended terms, and we have the attribute names and descriptions. Those of you who are going to be making your dataset available via SIOS, which will be many of you who are watching today, will also need to have a look at the page on the Arctic Data Center. They provide a list of attributes that you should be including if you want your data to be hosted by the Arctic Data Center, and they also happen to be the same attributes that you should be including if you want your data to be available via SIOS. So we have a list of terms here, and we can see that these are all actually compliant with the attribute conventions for data discovery and the CF conventions. So basically, instead of having a list of highly recommended and recommended terms, you now have a list of terms which are required or optional, which is a little bit less ambiguous. The next thing to have open is the CF conventions page, and we're going to open the latest release and a PDF of that. This file is quite extensive, but I went through some of this in another video where I introduced you to NetCDF files, so I'll put a link to that video down in the description and you can go and watch that if you need a catch-up. One thing that is going to be particularly important, however, is to have the CF standard name table accessible. So this is going to be a list of standard names that we should be assigning for each of our parameter names. So I'm going to put a link to all of these pages that I've mentioned down in the description, and I will flick back and forth between this and Python while I'm creating the file. So let's get stuck in. Okay, so the first thing we're going to do is import the modules that we're going to use today. We're going to import xarray, which is going to help us create the NetCDF file. We're going to import pandas, which is going to help us read in the data from Excel. And from datetime, we are going to import datetime, and we're going to call that dt, and that's going to help us to assign timestamps for our date created global attribute. The first thing we've got to do now then is to load our data. So we can create a data frame called data equals pandas.read Excel, and I'm working in the same directory as my data is, so I can just enter the file name there, and the sheet name of the data is conveniently called data. And we have our global attributes as well, so I'm going to write those to a data frame called global attributes in much the same way. I could probably have copied and pasted this, but the sheet name this time is going to be global attributes. I'll just try and run that to make sure that's loaded in correctly. And if I have a quick look in my terminal, at my console on the right hand side, we have the data here. We can see a number has been assigned to the temperature variable, and we have the global attributes here. And the next thing to do is to actually write our data to an xarray object, and I'll show you exactly how easy that can be. So we're going to call our object xrds, and we're going to make that equal to xr.dataset, so our xarray dataset. Open up some brackets, and within this we're going to have our coordinate variables. So in this case that is the depth, and this is going to be a dictionary, a Python dictionary, but in this case we only have one coordinate variable, which is the depth, and we're going to make that equal to our data and the depth column. If I run that now, and I will have a look on the right hand side of our object that we've created, and we can see here that we have our coordinates variable with our depth and the values here. We've also written a dimension, and we can see that there is a depth dimension with 7 points. You might be wondering why I've had to include a list. Well, if I don't, I will show you what happens. Rerun this. It runs just fine, but when I create this and look at it, we can see in this case we have two coordinate variables, and that's because our data frame has the index, which is 0, 1, 2, 3, 4, and also the depth values. So we'll put that back in. We also need to include our data variables when we're creating this, so we do that by calling this data vars equals, again, a dictionary and some circular brackets. And in this case we're going to call our first data variable practical salinity. So this is the variable name that someone's going to see. This doesn't have to be standardized, you can call this whatever you want. So we'll make that equal to, in circular brackets, I'm going to move that comment out of the way. The first thing we need to include in here is what dimension this variable has. So our practical salinity variable is going to have a dimension of depth. So we can include in square brackets the dimension name, depth. And we do this in square brackets because if this was multi-dimensional data, we would need to include multiple dimensions, so a list of dimensions. But in this case, we only have one value. Then outside of our square brackets, but still within our round brackets, we put comma, and then our data values. So data, our data frame object, and practical salinity. We can put a comma after this, and we're going to include a second data variable. It's going to have the same dimension, so I can copy and paste it, but I'm going to replace this practical salinity and I'm going to call it temperature instead. And the column name is also different, so we can call this temperature, which is our column name in our Excel file. And we need to make sure we have a comma between our two data variables. We don't need it at the end. And if I run this, and I'll have a look on the console again at the xarray object I've created, we can see it here. Now we have two data variables, the practical salinity and the temperature, and we have our coordinate variable. And we can see that each of our data variables has a dimension of depth. So we've linked each of our values to their respective depth coordinate values. A NetCDF file also includes global attributes, so we can assign those now. So how do we do that? Well, if we go back to our Excel file, what we can see is we have a table of attributes. So what we want to do is loop through each row in turn and write each attribute to the dataset. So we're going to write for index row in global attributes dot iterows, and then circular brackets and a colon. So what this is going to do is going to loop through each of the rows in the global attributes data frame, and it's going to write out two variables for each loop. One of them is going to be the row number, which is just going to be a counter 0, 1, 2, 3, and then it's the contents of each row into the row variable. Then to write each of those, we're going to write them to our xrds object, our xarray object. Going to write it as attribute, so attrs, and then we open square brackets, and what we need to assign here is the attribute name. So if we were assigning an attribute like title, we would just do this and then write what our title would be. But in this case we want to loop through each one, so instead of doing that we can just replace this title with row square brackets attribute, and we can also replace this with row value. So what we're doing here is looping through our global attributes data frame, and we're accessing the attribute term and the value term for each row. So we're taking the name of the attribute from the attribute column and the value that's going to be assigned for that attribute from the value column. Okay, let's run that and you'll be able to see the results. And if we write this again in the console, we can see now that we have a long list of global attributes that have been written. In this case we're only displaying 12 out of 34 of them, that's fine. We can have a look at the rest later. You'll remember also that there's a couple of attributes that we need to write that we left blank earlier, the date created attribute and the history attribute. According to the ACDD conventions for the date created, the ISO 8601-2004 extended date format is recommended. The ISO 8601 standards have their own Wikipedia page, and we can write it like any of these. For example, like this. So first thing we're going to do is write a dtNow variable, which is going to be the string of the time right now. And we're going to make that equal to dt, which is our datetime module, dot now in brackets. If we do that, that will be a datetime object. We don't want it in that format, we want it as a string. So instead we can then do dot strf time. And this is just where we list the format that we want our string to be in. So we can open quotation marks, and what we write is %sign in year, and that'll tell us to write the year as a 4-letter term, dash %month, dash %day, then we have T for time, and %h colon %m colon %s, and then a z, which denotes that this is a GMT time, so +00. Let's run that to make sure that looks okay. dt now, and we have our timestamp here. Now we need to write that out into our attribute, so xrds.attributes, and our attribute is called date created, and we'll make that equal to dt now. Then we also need to write our history attribute, so xrds.attributes history. We can see that this history term should provide an audit trail for modifications for the original data, and we should have a different line in our string for each time we modify the data set. So I'm going to write that now, and I'm going to do an f string. If you don't know what that is, appending f before your quotation marks allows you to write variable names within the string a bit more easily. So I'm going to write file created at, and then in squiggly brackets, dt now, and that's going to write our dt now variable. And I'm going to write using xarray in Python. I'm going to go and create a whole bunch of new lines so we don't run out of space and it's a bit easier for you to look at. And what we're going to do now is assign variable attributes. So what variable attributes are they're attributes that describe the variable, so each of our variable terms, so our practical salinity, the temperature, and the depth. This is done in a very similar way to how we assign our global attributes, but this time we write xrds and we tell it which variable we want to assign our attribute for. And then again, .attrs, I'll make this equal to a dictionary. So a dictionary in Python has these squiggly brackets. We of course can write this in this format as well, with the dict and then round brackets, but this is just another way to do it. So how do we know what variable attributes to assign? Well, this is dictated by the CF conventions, but confusingly I'm actually going to direct you to the ACDD conventions page, which has a nice overview of what attributes we should include. So if we go down to the bottom of this, so we can see here on the ACDD conventions page we have highly recommended variable attributes, and we can see that these are all recommended by the CF conventions. So we have a long name, which is our own description of the variable. We have the standard name, which is taken from the CF standard name table, which is here. We have the units, and we have the coverage content type. So in this case we're going to have coordinates for our depth variable, and we're going to have physical measurements for our temperature and practical salinity variables. But if this is a model result, you have a term for that as well. So let's write those. We have standard name. So to find what standard name we need to include, we need to write in here depth and see what standard names come up. And conveniently, the standard name for depth is just called depth, the vertical distance below the surface. So we're going to write that here, comma, and then our long name we're also going to call depth below sea level. Our units are going to be meters, and our coverage content type is going to be coordinates. For vertical coordinates like depth or elevation, we also need to have another variable attribute, and we can go to the CF conventions page, which will tell us about that. And we can see in section 4.3 there's some help about how to assign different attributes for the depth coordinate. And we can see here the direction of positive is useful for applications displaying the data. For this reason, the attribute positive, as defined in the CORD standard, is required if the vertical axis units are not valid unit of pressure. So in this case, we should be assigning positive equals down. because our values of depth increase as we move down below the sea surface. So we can write that as well, positive down. I'm going to write that now so you can see how it looks. So in the console, I'm going to write xrds and depth. If I print that, you can see we have different attributes for our depth coordinate variable. Our other variables are going to have 4 of the same attributes, so I can copy and paste this. I need to finish off my curly brackets here. I can remove this comma at the end because I don't need it. They're both going to be physical measurements. I can remove the units, the long name, and the standard name. And I can remove the variable name. Actually, if I go back and check on the ACDD conventions, we can see that this should be physical measurements and not physical measurements. So I'll remove the S. I'll make 2 copies of this, one for our temperature variable and one for our practical salinity variable. So the first, temperature, the second, practical salinity. So for temperature first, let's go and see what our standard name can be. So we return to the standard names table, and this time we're going to have a look for temperature of sea water. And we can see that there's actually 48 standard names matching this query, so we need to select the right one. Fortunately, I know which one that is. We can go to sea water temperature, and if we're in any doubt, we can read through this description. And for someone using this data later, they might see that this sea water temperature standard name has been assigned. If they're in any doubt as to what that is, they can come to this page, do the same search that we have, and read this description so that they can understand exactly what those data represent. Of course, this is quite a simple example, but there's some standard names which are somewhat more complicated. So let's go back to Python and assign the standard name sea water temperature. Make sure you get your spelling correct. For long name, we can assign whatever we want. This is somewhat redundant here because this is quite self-explanatory, but we can write temperature of sea water. And our units in this case are degrees C. Let's do the same for our practical salinity. Practical salinity of seawater. We have our term here. We can read the description and make sure that this is correct. And then we take our standard name. And actually I'm going to copy and paste this across to make sure that I'm not spelling this incorrectly. So the long name, again, I can write practical salinity of sea water or whatever else I want to write. The units of practical salinity are PSU, the practical salinity units, but that's the same as parts per thousand, so we can just write 1e minus 3. And the last thing we're going to do here is specify the encoding. So what we're going to be doing is telling the dataset exactly what format we want each of our variables to be written out in. So we can specify the encoding in a dictionary. I'm just going to call this dictionary my encoding. And we have to specify the encoding for each variable in term. So we have a nested dictionary here where we can specify each term in the encoding for that variable. Let me scroll down a bit. The first thing is the D type, which is the data type. Our values are going to be integers, so 1, 2, 3, 4, etc. So the format is int32. And the other thing we need to assign is whether we have a fill value and what that is. In this case, because this is a coordinate variable, there should be no fill value. And that's because there should be no missing values in your dimensions. We could do the same for temperature. So again, we make this equal to a nested dictionary. We have our D type, and this time it's going to be floats. So floats are numbers that also have decimals. In most cases, float 32 is fine. If you have a lot of decimal places, you might need to specify the data type as double. But in this case, float is fine, and this will take up less space. We are going to assign a fill value here. Remember the leading underscore. And this fill value is a common value that's going to be assigned every single time you have a missing data point. And we're going to assign an unrealistically high value here. The advantage of this approach is that we're explicitly telling our data user that no data have been collected here. If we were, for example, just to leave it blank and assign no fill value, this could leave some ambiguity as to whether we have just forgotten to assign a value in this case. This is telling our user that we have no value. Perhaps we intended to take a value here, but it didn't work, and so we're assigning a fill value instead. I missed my comma here. And we're going to assign one more term here. We're going to call that zlib, and we're going to write false. So this is just telling xarray that we don't want to compress our values in this case. Our practical salinity is going to be exactly the same as our temperature, so we can just copy and paste this, put a comma in between, and change temperature to practical salinity. And then we're ready to output our data. So we can write xrds dot to NetCDF. We can give it a file name, dummy data depth profile in this case, .nc. You should give it something a bit more descriptive, and we'll specify the encoding equals my encoding. And if I run all this, our file should have been created. I'm going to show you a different way to look at your NetCDF file, and that's using some software called Panoply. So Panoply is some software that's been developed by NASA. It's quite widely used by people to look at NetCDF files and provides you with a way to quickly visualize your data. It's available in Mac, in Windows, and in Linux, so you can go here and download it, and I'll put a link to this page down in the description. When you launch Panoply, it looks a bit like this. You have a window where you can navigate to the file that you want to open. So we're going to open this here. This is all a bit bright, but if I highlight this, we can see a printout of how our NetCDF file looks, all the attributes. It also has nice features for actually visualizing the data. So we have our variables here. If I click on the practical salinity, we can see our practical salinity variable attributes. But if I right click and write create plot, it tells us here a line plot using depth for the horizontal axis by default, but I want to change that to vertical. If I hit create, we can see our depth profile of our practical salinity data. And if I select on array 1, we can see our values too. We could do the same for our temperature. Create plot, depth for the vertical axis, and in this case we can see we have some missing values. And we go to array 1, we can see that what Panoply has done, we can see that it's identified the fill value that we've assigned, and it's automatically removed that and just replaced it with an NaN. So it's done the work for us. There's even here actually a pretty nice option where you can right click and export the data to CSV. So if you find someone else's NetCDF file, if you're not that comfortable with Python or R or any other method, you can just open it up in Panoply and export the data to CSV for you to use. And that's everything. If you've got any questions, leave a comment below. Thanks very much for listening.